A black hole is a region of spacetime where gravity is so strong that nothing, including light and other electromagnetic waves, has enough energy to escape it. The theory of general relativity predicts that a sufficiently compact mass can deform spacetime to form a black hole. The boundary of no escape is called the event horizon. Although it has a great effect on the fate and circumstances of an object crossing it, it has no locally detectable features according to general relativity. In many ways, a black hole acts like an ideal black body, as it reflects no light. Furthermore, quantum field theory in curved spacetime predicts that event horizons emit Hawking radiation, with the same spectrum as a black body of a temperature inversely proportional to its mass. This temperature is of the order of billionths of a Kelvin for stellar black holes, making it basically impossible to observe directly. Objects whose gravitational fields are too strong for light to escape were first considered in the 18th century by John Michel and Pierre-Simon Laplace. In 1916, Karl Schwarzschild found the first modern solution of general relativity that would characterize a black hole. David Finkelstein, in 1958, first published the interpretation of black hole as a region of space from which nothing can escape. Black holes were long considered a mathematical curiosity. It was not until the 1960s that theoretical work showed they were a generic prediction of general relativity. The discovery of neutron stars by Jocelyn Bell Burnell in 1967 sparked interest in gravitationally collapsed compact objects as a possible astrophysical reality. The first black hole known was Cygnus X-1, identified by several researchers independently in 1971. Black holes of stellar mass form when massive stars collapse at the end of their life cycle. After they form, black holes grow by absorbing mass from their surroundings. Supermassive black holes of millions of solar masses may form by absorbing other stars and merging with other black holes. There is consensus that supermassive black holes exist in the centers of most galaxies. The presence of a black hole can be inferred through its interaction with other matter and with electromagnetic radiation such as visible light. Any matter that falls onto a black hole can form an external accretion disk heated by friction, forming quasars, also called active galactic nuclei, which are some of the brightest objects in the universe. Stars passing too close to a supermassive black hole can be shredded into streamers that shine very brightly before being swallowed. If other stars are orbiting a black hole, their orbits can be used to determine the black hole's mass and location. Such observations can be used to exclude possible alternatives such as neutron stars. In this way, astronomers have identified numerous stellar black hole candidates in binary systems and established that the radio source known as Sagittarius A, at the core of the Milky Way galaxy, contains a supermassive black hole of just over 4 million solar masses. On the 11th of February 2016, the LIGO Scientific Collaboration and the Virgo Collaboration announced the first direct detection of gravitational waves, representing the first observation of a black hole merger. On the 10th of April 2019, the first direct image of a black hole and its vicinity was published, following observations made by the Event Horizon Telescope in 2017 of the supermassive black hole in Messier 87's galactic center. As of 2023, the nearest known body thought to be a black hole, Gaia BH1, is around 1,560 light-years, or 480 parsecs, away. Though only a couple dozen black holes have been found so far in the Milky Way, there are thought to be hundreds of millions, most of which are solitary and do not cause emission of radiation. Therefore, they would only be detectable by gravitational lensing. The no-hair theorem postulates that, once it achieves a stable condition after formation, a black hole has only three independent physical properties: mass, electric charge, and angular momentum. The black hole is otherwise featureless. If this conjecture is true, any two black holes that share the same values for these properties, or parameters, are indistinguishable from one another. The degree to which the conjecture is true for real black holes under the laws of modern physics is currently an unsolved problem. These properties are special because they are visible from outside a black hole. For example, a charged black hole repels other light charges just like any other charged object. The total mass inside a sphere containing a black hole can be found by using the gravitational analog of Gauss's law, far away from the black hole. The angular momentum, or spin, can be measured from far away, measuring the frame dragging effect caused by the gravitomagnetic field. When an object falls into a black hole, any information about the shape of the object or distribution of charge on it is evenly distributed along the event horizon of the black hole, and is lost to outside observers. The behavior of the horizon in this situation is a dissipative system that is closely analogous to that of a conductive stretchy membrane with friction and electrical resistance. This is different from other field theories such as electromagnetism, which do not have any friction or resistivity at the microscopic level because they are time reversible. Because a black hole eventually achieves a stable state with only 3 parameters, there is no way to avoid losing information about the initial conditions. The gravitational and electric fields of a black hole give very little information about what went in. The information that is lost includes every quantity that cannot be measured far away from the black hole horizon, including approximately conserved quantum numbers such as the total baryon number and lepton number. This behavior is so puzzling that it has been called the black hole information loss paradox. The defining feature of a black hole is the appearance of an event horizon, a boundary in spacetime through which matter and light can pass only inward and will inevitably reach the singularity at the center. Nothing, not even light, can escape from inside the event horizon. The event horizon is referred to as such because if an event occurs within the boundary, information from that event cannot reach an outside observer, making it impossible to determine whether such an event occurred. Another way of saying this is that at the event horizon, the escape velocity exceeds the speed of light. As predicted by general relativity, the presence of a mass deforms spacetime in such a way that the paths taken by particles bend towards the mass. At the event horizon of a black hole, this deformation becomes so strong that there are no paths that lead away from the black hole. To a distant observer, clocks near a black hole would appear to tick more slowly than those farther away from the black hole. Due to this effect, known as gravitational time dilation, an object falling into a black hole appears to slow as it approaches the event horizon, taking an infinite time to reach it. At the same time, all processes on this object slow down, from the viewpoint of a fixed outside observer, causing any light emitted by the object to appear redder and dimmer, an effect known as gravitational redshift. Eventually, the falling object fades away until it can no longer be seen. This process usually happens very quickly, with an object disappearing from view within less than a second. On the other hand, indestructible observers falling into a black hole do not notice any of these effects as they cross the event horizon. According to their own clocks, which appear to tick normally to them, they cross the event horizon after a finite time without anything odd occurring. In classical general relativity, it is impossible to see the event horizon from nearby the black hole, due to Einstein's equivalence principle. The event horizon of a black hole at equilibrium is always spherical, while for rotating black holes the event horizon is more squashed, due to centrifugal force caused by the black hole's rotation. The faster it spins, the more squashed it will be. At the center of a black hole may lie a gravitational singularity, a region where the spacetime curvature becomes infinite. For a non-rotating black hole, this region takes the shape of a single point with 0 dimensions and 0 volume. For a rotating black hole, it is smeared out to form a 2-dimensional ring singularity that lies in the plane of rotation, with a measurable greater than 0 radius. In both cases, the singular region has 0 volume. It can also be shown that the singular region contains all the mass of the black hole solution. The singular region can thus be thought of as having infinite density. Observers falling into a Schwarzschild black hole, which is non-rotating and not charged, cannot avoid being carried into the singularity once they cross the event horizon. They can prolong the experience by accelerating away to slow their descent, but only up to a limit. When they reach the singularity, they are crushed to infinite density and their mass is added to the total of the black hole. Before that happens, they will have been torn apart by the growing tidal forces in a process sometimes referred to as spaghettification or the noodle effect. In the case of a charged Reissner-Nordström or rotating Kerr black hole, it is possible to avoid the singularity. Extending these solutions as far as possible reveals the hypothetical possibility of exiting the black hole into a different spacetime with the black hole acting as a wormhole. The possibility of traveling to another universe is, however, only theoretical, since any disturbance will destroy this possibility. It also appears to be possible to follow closed time-like curves, returning to one's own past, around the Kerr singularity, which leads to problems with causality like the grandfather paradox. Every object with mass has a Schwarzschild radius, and if the object's radius ever exceeds its Schwarzschild radius, it will collapse into a singularity, with the Schwarzschild radius become the location of the event horizon of the new black hole. As a side note, the appearance of singularities in general relativity is commonly perceived as signaling the breakdown of the theory, in other words, a place where the maths fail to work. This breakdown, however, is expected. It occurs in a situation where quantum effects should describe these actions due to the extremely high density. Until today, no one has been able to combine quantum and gravitational effects into a single theory, although attempts have been made to formulate such a theory of quantum gravity. It is generally expected that such a theory will not feature any singularities. This is the end of part 1 of the Black Hole series. Subscribe to the Wiki Hole and check out part 2 and other videos about the most interesting topics in science.